All right, let's start. Okay, so all right, so I was hoping to get the homework out yesterday, but it turns out we had other stuff to do, so I'll have it out by tomorrow. Okay, so that's yeah. Sorry for the slight delay. It'll still be due 2 weeks from whenever I release it, but it's just couldn't do it yesterday. Okay. All right. So yeah, this is the announcement I had last time too. I still have it because I forgot to put it up on the course page. So that is. Those are the same announcements as last class. Alright, so what did we do last class? So we saw a simple greedy algorithm for the minimum spanning tree problem. Okay, and so the algorithm was essentially it was adding one edge at a time. So recall this was a graph problem where you had a bunch of vertices, you had a bunch of weights for edges, and you wanted to pick a set of edges that had the smallest weight so that everybody is connected. We said that the best way to pick it is pick a tree which has the smallest cost. Okay, and right, and the way we did that was essentially add one edge at a time. Okay, so this was the algorithm. Yeah, and what we saw last time is that in some sense the algorithm is easy, right? Like some of you came up with it, but the analysis was a bit more tricky, right? So. Yeah, some of you had questions about the analysis, so I just wrote down some notes. Hopefully they are clear. Okay. So read those. But the thing to remember is that it's an example of a meta argument that is actually kind of useful in reasoning about greedy algorithms more generally. Okay, and the argument is essentially that you prove inductively that there exists a optimal solution, there exists some optimal solution that contains all the greedy choices you've made so far. Okay, and this is a useful meta argument that works for a bunch of greedy algorithms. Okay, where you say that I mean your greedy algorithm is making a bunch of choices. You say that there is some optimal solution that contains all the choices you have made so far, okay, and possibly something else. So, and then when you prove this inductively at the end, you'll have that there is an optimal solution that contains everything. Okay. And this is we saw this kind of argument in last class's proof. Right? So we said that it was important to start with the spanning tree for the full graph that contains the edges you've chosen so far. And yeah, so it turns out there are a couple of other problems for which the same meta reasoning works. Okay, so we'll see an example of this. I will post a note on this, but there's another popular. So I will post a link to Jeff Erickson's note. I mean, the link is already there, but the specific section. This is about a problem called interval scheduling. It's very similar. Okay, so the argument goes by saying that there's always an optimal solution that extends, in some sense, the stuff you've picked so far. So that's yeah. So this is a clean meta argument. So today we're going to see another example. Okay, so the plan for today, I forgot to write a slide for this, is essentially we're going to look at another example of greedy algorithm where what you have won't quite be optimal, but it will be somewhat close to optimal. Okay, so we'll see an example of this. And this will be your first introduction to what are called approximation algorithms. Okay, so we'll see an example of that today. And Yeah, and then after this we'll go to a related paradigm to greedy for local search. So that's the plan for the day. Okay, so let's see. So here's a slightly different problem. Okay, yeah.
So what do you mean by inductively prove that there is a...
So you prove using induction. That's all.
Like do we assume or...
No, so you assume the base case, right? Like you prove using induction that there is a solution that contains the subset that you have chosen so far. Okay? And initially you would not have chosen anything, so the claim is vacuous. It's vacuously true. And you have to prove the inductive step. Like if it is true for a certain thing, it is true for the next step. Okay, and this is what we showed last time. Right?
You
Like,
don't assume from the beginning that there exists an optimal solution.
I mean, you can assume there exists some optimal solution, but what we are trying to say is that there is an optimal solution that includes all the choices you have made so far. Okay, so think of it as optimum is something we have no idea about, right? And we have this greedy algorithm that's sequentially making choices, and you want to show that that this is optimal. What this produces is optimal. So what you will say is, okay, suppose my first choice was the edge E1. Okay. Then you'll say there is an optimal tree for the full graph that includes the edge E1. Okay. And then suppose the next choice was E2. Okay. Then you will say that, okay, there is an optimal solution for full graph that includes both E1 and E2. And so on. Okay. So you always have the solution picked so far. You prove that there is an optimal solution that includes the stuff you've picked so far, all the things you've picked. So this may seem strong, but this, if the greedy algorithm actually produces an optimal solution, usually this would be a good way to do it. All right. So let's look at a different problem, okay, where the analysis will also be quite different. So I want to give you a taste of different kinds of analyses. So that's why we're seeing a bunch of examples. Okay, so the first analysis we did for the scheduling problem was rather easy. Last class's analysis was somewhat tricky and it introduced this different paradigm. Now we'll see a more combinatorial, very direct analysis. So sometimes these kind of things work. Okay. All right. So the problem is the following. Okay, so you've got n people, let's say, and you have a set of skills that will that come from the universe 1 through m. Every person has some subset of these skills. You have m different skills. Let's take something like math and rowing or something. Just think of very different skills, right? So, and every person has a subset of these skills. And you want to pick, your goal is to pick k people so that you maximize the total number of distinct skills. So, right, so this is a somewhat natural problem. You can think of many motivations for this. Right? So this is the goal. Okay, so you want to pick k people so that the total number of distinct skills they have is maximized. So there's no real point if two people happen to have the exact same skill set. You don't want to pick both because you have a budget of k people and you want to pick you want to maximize the number of distinct skills. Right? So formally, for every person, you can think of the skill set as this Si, which is a subset of 1 through n. And what you want to pick is some k of these sets Si so that their union is maximized. So union is the number of distinct. Right, so what is a natural greedy algorithm for this problem? Well, let's say you want to build up a solution. Right? So how would you solve this problem in a greedy way? Yeah?
Choose whichever person first, then remove other things skills of this person.
Okay, so what he's saying is, okay, yeah, and how do you proceed?
And then choose the next one and most different.
Okay, so what he's saying in some sense is, so you first choose someone, okay? I mean, why an arbitrary person? You might say, I will choose a person who has the most number of skills to start with. That sounds like a more... No, M is large. Yeah, so both M and the number of... Yeah, so... Okay. So actually, in this problem, it's nice to have... think of a bipartite graph. Okay, well, on the right you have the skills. On the left you have people, N let's say, and you put an edge if person I has this skill J. So this could be like if S1 is 1 is 2, 3 and something else, then I have this. So you can construct a bipartite graph. So I think what he's saying is you first pick some person. And maybe you pick the one, I mean, it's a natural choice to pick somebody who has the most number of skills, because your goal is to maximize the number of skills. Okay, so you pick, start with person with most number of skills. Okay, and suppose it is this person. Suppose it is 1. Okay. And now you know that in some sense you've covered these skills. Right? So if any other person, for any other person, the new value that this other person is going to add to your union is the number of skills he has that are not the ones that are already marked. Okay. So update. What you're going to do is update the value of all the others. So yeah, maybe this is a bad word, but you don't want to treat people as just giving some value. But yeah, for the purpose of the algorithm, so you update the value that this person is going to add, given the ones that are already covered. It is the number of skills this person has that are not the skills that were already covered. Okay, so that's the. So and now pick person with max value and repeat. So now you've and this person will have covered a bunch more skills, so you mark them also as covered, and you update the value of all the rest and pick the person with the max. Okay, so this is a natural greedy process, right? So any questions about the algorithm?
So would the value be like number of new skills that they contribute or something like that?
Yeah, so let me just write it down. So value of I is number of elements in Si that are not in the sets chosen so far. Okay, so let's give a name for the sets chosen. Okay. So maybe you picked S1 and S3 so far. Then the new value of I will be number of elements in Si minus the intersection. So say we picked S1 and S3 so far. Yeah, then value of a vertex I would be the size of Si minus S1 union S3. Okay, so this is the natural. And pictorially, it is just the number. Suppose we are marking the skills we've seen so far with a tick mark. Then for a new vertex, this is the value is the number of edges this person has to vertices that are not ticked. So it's the obvious thing. All right. So question is, how good is this algorithm? Right? Like you can pick k vertices like this. Okay. And as usual, we break ties arbitrarily. Okay, so you might ask, can you break ties in some clever ways? And usually these kind of analysis don't change too much. Well, if you break ties in most natural ways. Yeah. What do you mean?
So if I pick all of them, that will maximize.
Oh, no. So k is given. So k is given, and it is something which will presumably be much less than n. Okay. Now, if k is n, the problem becomes easy. But we want to argue about it for every k. So, yeah, k is part of it. Yeah, k equals 1, k equals n, these are trivial cases. Alright, so this is that, right? So now, right, so is this optimal? And takes a little bit of thought, but an example like this shows that it need not be. Okay, so if you have a bunch of sets like this, so this is S1, this is S2, S3, S4. Okay, and if your k is 2, then if you just think about this algorithm, the first you'll end up picking S1. You could have picked S1 or S3, but you break ties arbitrarily, so therefore you pick S1, let's say. Okay. And so you pick S1, and then picking either S2 or S4 gives the same value. So let's say you pick S2. Actually, any one of these three things gives the same value. So let's say you pick S2. So greedy will pick these two, and their union has a size of 4. So the union of S1 and S2 is just 1, 2, 3, 4. So this union is S4. But the optimum is of course to pick S3 and S4. And yeah, because you were breaking ties independently, you ended up picking S1 first, and that was the mistake you made. Yeah. Do you have a question? Oh. Yeah?
If we didn't tell every each set has no element, I mean, we also have S4 with 5, right? So we need to have another repeat rule of S4 for the greedy algorithm. Is that right?
What do you mean?
I mean, after we pick S2,
Yeah.
S4 is also with 5, right?
Right, but your k is 2, right? And you've already picked 2 elements. So you are supposed to pick exactly 2 elements. 2 of the people, right? So yeah.
Right.
So once you've picked, maybe I should say repeat k time. So this thing is repeat k time. Maybe we'll go to repeat k. Right. So you end up, you stop when you've picked k. So this is okay. So this is not optimal, right? So in this case, you've got the union has size 4, but the optimum is size 5. So all right. So now, okay. So now you can ask the question: is this? I mean, do we give up all hope? I mean, is this algorithm just basically worthless, right? And so you can ask, can greedy be really bad? This was an example where it was 5 versus 4, right? So greedy was doing 4, your optimum was 5. And typically, I mean, for some problems, greedy can be like really bad, because it can be like way off top. But there are problems, actually for many problems, you can still show something interesting about greedy algorithms. Okay, and that's what we will see here. So our answer to this would be no. Okay, so greedy cannot be like too bad, and the way we formalize this is by saying the value of the solution produced by greedy is at least. Okay, so this is the theorem we're going to show. Okay, that greedy may not be optimal, but it's not terrible. Okay, so this is and this is the approximation factor we will get. So in fact, what we get will be a little bit stronger. It will be something like 1 minus 1 by e. Okay, where e is the usual base for the natural logarithm. Okay, so this number that will be 0.63 something. So the approximation factor, so you'll always get a solution whose cost is at least 0.63 times the value of the optimal solution. Okay? So it can't be, for instance, 10% of the optimal. Okay, so it will be at least 63% of the optimal. And this is a non-trivial statement, right? Because we have no idea what the optimum is, but we can somehow prove that whatever we are producing by this greedy algorithm is not too far from it. So that's why, yeah, in general, approximation algorithms are difficult, because computing the actual optimum is could be hard. Like in this case, this problem turns out to be hard for those of you who know, and but we are still able to come up with a solution that is reasonably good. Yeah, these kind of algorithms are called approximation algorithms. And yeah, this is the first example we are seeing of. Alright, so how do we prove such a thing, right? Such a statement. And so we want to, yeah, so we should try to, I mean, okay, what we've seen last class is trying to say that in some sense there is an optimal solution that includes the things we've picked so far. But would you expect such a statement to be true? I mean, would you expect it to be true as is? Yes, yes. So last class what we said was there exists optimum solution for the full problem that includes the choices you've made so far. Yeah.
I think that's true. And then you could see an example of
Yeah, so you could, so what he's saying is, this can't be true, because if this were true, it would imply that greedy actually finds the optimum solution. Because in the end, this argument will say that there is an optimal solution that contains the stuff we've picked, and that would mean that in this example you would have picked the optimal. So this we can't hope that this is true, because we know that greedy is not optimal. So we need something a little bit weaker, and you might guess that okay, maybe I can prove that there exists an optimal solution whose cost is not much worse than what we've picked so far. So these kind of reasonings sometimes work, but I don't think this can be made to work for this problem. Okay? So to the best of my knowledge, you can't prove the inductive statement very well. Okay, so we'll use a slightly different argument here. We'll use a more direct argument. And turns out, okay, so which is not particularly hard to come up with. Okay, so the idea is, what can we reason about the first step, right? So we have greedy, okay, and this is picking sets in some order. Let's say it picks set Si1 first, and then Si2 next, and so on to Sik. Okay, so it proceeds for k iterations. Each time it picks some person, so some set to add. Okay. And I'm just giving names for this. So let's say greedy picked these guys. Okay. And suppose their union. Okay, so I'm just defining some notation. Okay. So I will call the union of, this one I will also call it as y1. The union of these two I'm going to denote by y2, and so on. The union of everybody we've picked, I want to define as, I just want to give it a name. Okay, so this is just to simplify notation later. And I want to show that, so what is the objective value? So this is the union of all of this here. Okay, that's yk. Okay, so yj is defined to be Si1 union Si2 union so on until Si. Okay. So this is 2 in this. Yeah. So what is the cost of the solution you've picked? What is the value of the solution you've picked? Sorry? Yeah, so the value of the solution you've picked is exactly the size of yk, right? Because that's how we're measuring the value. Okay? Right here. So the value of solution by definition is size of y. It's just the union of all the size of the union of the stuff we picked. Alright, so let's now think about what the optimal solution is. Okay, so the optimal solution will pick some different sets, right? So it will pick a bunch of sets, and those guys will have some union. Okay? So let the unions of the optimal set be something which I will call right. So we denote it U. So U is some subset of 1 through m, and this is a union of all the optimal sets. And actually, let's give a name for these optimal sets, and let's call them SR1, SR2, So these are just R1, R2 up to Rk are the optimal set of people, okay, that who actually maximize the union of their skills. So this is these are so this is just notation so far, and I'm denoting by U the union of all these things.
Sorry, so these SR1s are like a subset of the optimal set, or
No, so these are, remember, the optimum is also, so we want to pick k people or k of these SIs that maximize, so that their union is maximized. Right? So I'm just saying, suppose the optimal was something like 1, 3, and 1, 3, and 5. Then my R1 is 1, R2 is 3, R3 is 5. I'm just giving the base. Some people get confused with multiple sub-indices, but there's nothing to fear. What's there? It's pretty simple. Okay. Yeah. So these are the optimal sets. I'm just denoting them SR1, SR2, SR. Alright. And their union is denoted by U just because I want a name. And size of U is the, so in some sense, so our goal is to prove that size of yk, goal rephrased in this notation, is that size of yk is bigger than or equal to half. I'm writing half because the formal theorem I wrote said half. Okay, half of size of so in this notation, this is just our just rephrased. Alright, so why did I introduce so much notation? Okay, so I want to start by doing something inductive, right? So what can I say about y1? Can I say that y1 will be reasonable as a function of size of u? Does this make sense? Yeah.
Well, I guess you're just saying y1 specifically. Well,
Yeah.
that exact, like that will actually be exact because it's the first step. So you can't really screw
No,
up.
it will be optimal with respect to k equals 1, right? But what I'm asking is, can you relate the size of y1 to u, which was the union of the optimal sets for k? Right? So, but the idea is right? So you want to say that y1 cannot be too tiny. Okay, so what is a trivial bound you can get for y1 as in terms of size of u?
U divided by k greater y1
Okay.
greater than
So
u.
what do you, yeah. So claim is, let me create a new page because. Okay, so the claim is that size of y1 is bigger than or equal to size of u divided by k. So given this, can somebody else say why this has to be true? So his claim is that the first set you pick will have a size that is at least size of the union of these guys divided by k.
If everyone had the same number of skills, you're essentially saying it's got to be at least greater than or equal to. Either it has the same number or more than, you're picking
Okay.
one of the
Yeah.
lowest numbers.
So his inclusion is the right one, right? Like in some sense, he's saying that if the union of these SR1, SR2 to SRK is U, then one of them should have size that is at least size of U divided by K. Because if all of them had size of U, had size strictly less than this, then you can't have a union whose size is bigger than the sum of its parts, right? Or something like this. Okay, so because these guys can only have overlaps. So okay, so size of union, size of U is less than size of SR1 plus so on the size of SRK. Therefore, one of them is bigger than or equal to U by K. Okay, so one of these guys is bigger than. So what his argument said is that one of these guys has size bigger than size of U by K. But now, why is the greedy algorithm's choice bigger than size of U by K? Yeah.
We are choosing the subset having the maximum number of skills getting off.
Okay, because the greedy algorithm by choice is picking the set that was covering the largest number of skills, right? So in particular, greedy could have chosen this particular S, okay, but it chose to choose. It chose to pick SI1, which means that size of SI1 is bigger than or equal to one of them. Say, let's call it S something. S prime is bigger than. Therefore, choice of greedy is only better. Yeah, this is the important step, right? Because greedy will actually look at everyone and is picking the one that adds the most value. Okay, so greedy would have had a choice of this particular S prime, but it chose to pick SI1. So it's only better, i.e. size of SI1 is bigger than equal to size of S prime. And this is equivalent to saying size of Y1 is bigger than or equal to the size of S prime, which is at least U by. So in the first step, the set you chose is not terrible. Okay, so it's at least size of U divided by K. Now, what can you say about the subsequent steps? Could you say something similar? Okay, so can you now use this sort of an argument to say that size of Y, let's say 2, is something which is a little bit bigger than size of Y1? So let me write down a claim, okay, about Y2, and now you guys can try to prove it inspired by the proof here. Okay, so the claim is size of Y2 is bigger than or equal to size of Y1 plus size of U minus Y1 divided by. So the next set you add, okay, so the number of new elements you have, okay, so will be at least, so Y2 minus Y1 is basically the number of new elements you've added, right? And I'm claiming that the number of new elements you add is at least U minus Y1 divided by K. Why is that? Yes, first try to understand what the claim is trying to say. So, that's the thing I have to show both these pictures. But yeah, so Y1 was, remember, first set you pick. Y2 is the union of SI1 and SI2, the union of the first two. So in some sense, I'm saying that size of the new stuff in SI2 has size at least U minus Y1 divided by K. And intuitively, it is similar to the previous argument, but how do you reason about it?
That's a good question.
Uh-huh.
How is it that you're divided by k? It's 0 by k minus 1, since you've already chosen 1 by k.
Yeah, that is a good question, but I don't think this statement is true if you had a k minus 1. Okay. So it would be nice if you could show k minus 1, but yeah, I don't think it should. Right, but that should give you some hint, right? Because it's yeah, so one of the nice things about this argument is that it does not tell you that whatever you pick in the end will have any overlap with you. Okay? It's a very funny argument, I mean, in the sense that whatever you pick, the sets you pick in the end may be completely disjoint from you. Okay? So U is your optimal set, right? So think of a case where, of this problem where you have two optimal solutions, both of which are completely disjoint, right? Like let's say you have 2k disjoint sets, all of the same size. So this is maybe for you this picture is confusing, but if you've got the union of so this is the element, the skills, right? So I'll write them in the same way. So you've got the skills 1, 2, 3 up to m. These are the skills. And let's say I've got 2k disjoint sets like this, groups of skills. Okay. And a person maybe has this skill, another person has this skill, another person has this skill. So the optimum in this case for k again is just this, right? Is any k of them will have the same size for you. The point is that now you could have chosen somebody who, like completely different optimal solution by following the greedy argument, because you're breaking ties arbitrarily. Okay. So in some sense, the argument must hold even with this kind of a setting, right? So in this kind of a setting, so you can't rely on your the SIs having any overlap with the optimal U. So yeah, so that's a clean, yeah, so that's the nice thing about this argument. Never uses the fact that you are actually finding the optimal set of skills. So you could be picking some stuff that is totally orthogonal, but all you can show is that the size of the sets you pick is not too small. And that's the nice thing about it. And alright, so since we had the picture, let me draw it again nicely. Okay, so you had all your set of skills. Let's suppose U was this, okay, and just drawing them nicely so that U comes up. Okay, so U was this. And suppose the stuff you picked were, I said they could be completely disjoint, but in general they might have some overlap. Right? So let's say Y1 was, it had a little bit of overlap, and this was Y1. So U minus Y1 is these guys. Okay. So Y1 is this, which means that S1 can be picked, sorry, Si1, the things that will be picked was covering these. Now I want to say that there is some set out here that whose uh, so I want to say that there is some set for which the number of new skills or there is some user such that the number of new skills this user has apart from y1 is at least that u minus y1 divided by k. Why should that? Like, can you use the optimum again in some way? I'll give you guys a hint. Okay? Can you show that one of these sets must actually have the overlap with this red portion being at least this one? Yeah, so this is takes a while. So U is the blue set that I've drawn. Y1 is set we've covered. Red is the stuff that remains. Yeah.
Can you kind of like do a like proof by contradiction? I think like if you like suppose that the second part, which is if the second part the u minus the elements from y1,
Yeah.
suppose that I guess I can't quite get it right, but
I mean, the question you should ask yourself is, okay, so what is U, right? U is just the union of k of these sets. K of these sets, which are like these SR1, SR2 to SRk. So let's complicate this picture a bit further. So what we are saying is U is formed out of a bunch of these sets. So maybe S1 is this, S2 is this, and so on. So in particular, these SR1, SR2 up to SRk, they cover all of U. Therefore, they also have to cover just the red part of U. Right? So remember, I mean, we are trying to say something simple, right? So there is this red part of U, and there is the part that is already covered by Y1. Okay, so U was this blue set. So there's a part that's covered by Y1, there's a red part. You know that SR1, SR2 up to SRk cover the whole of U. So in particular, they also cover the whole of the red part. Therefore, one of the sets among these SR, R1, R2 to Rk must have a size whose overlap with that red part is at least the size of that red part divided by k. And this is the exact same argument we've used here, right? Because we said at least one of the sets has size that is size of U divided by k. Now I'm using that argument just with the red part, okay? With this red part. So think about this a little bit. But so this is all I'm saying. Okay? So this is all this lemma is saying. Okay? That the exact same argument to prove is that this is the exact same argument as above, but with just the red portion. The red portion by definition is just U minus Y. Okay, so this is that. Okay, so now you get that y2 is bigger than equal to y1 plus u minus y1 divided by q. And yeah, and now it's fairly simple. Now you can show, okay, so this is a simple exercise for you guys. So this continues. Okay, so you get a that for all j, okay, y j plus 1 is bigger than the size of yj, sorry, yj plus this u minus yj divided by q. And this is, yeah,
Is it true that y1 is exactly SR? And then you can make the same thing with a minus 1? Because,
no, because you could have chosen a totally different set. And that's what I was saying, right? So you could have, but all you know is that the size is big enough.
No, I'm saying if y1 was exactly SR.
Yeah.
So you make the same thing.
Have at least y1 will be at least the average of y0 and u, which is this midpoint. And then, so y1 is at least over here. It's somewhere on this side. And then you have the average of y1 and u again. So y2 is at least over here and so on. So, I mean, if you want, the math is very simple. So you can prove by induction that if you had this equation, then size of yi will be bigger than or equal to 1 minus 1 by 2 to the I times size of t. So, yeah, if you had this equation, this you can prove very easily by induction if you don't see the intuitive one. But in general, what you can claim is, yeah, so let me write down, this is just straightforward manipulation, so let me not spend too much time on this. So what we showed is that yj plus 1 is bigger than or equal to size of yj times 1 minus 1 by k plus size of u times 1 by k. And this turns out to be some weighted average of this number yj and u. And you can use this to show that, okay, so maybe I'll just write the inductive claim. Is that size of yj is bigger than or equal to 1 minus so the way to think about it, the way to think about it is that the distance from u keeps reducing by 1 minus 1 by k factor. Okay, so you've got these numbers, y0 is 0, there is this size of u here, which is your target, this is how much you want to achieve. And you can get that initially the distance is this, the next step, you know that y1 is at least 1 by k times size of u, so your distance reduced by at least a factor of 1 minus 1 by k. The next step you can say that this will reduce by another factor of 1 minus 1 by k. So, yeah, so let me not dwell on this, it's just algebra. Okay, so you can prove this. So, intuitively, distance to u drops by at least a factor of 1 minus 1. Okay. So what do I mean by distance? Distance of side of y to u drops by. So yeah, so many of you don't seem convinced, but this is just standard algebra. So I expect that if you think about this a little bit, you'll be able to agree. Yeah, maybe I'll pause here anyway. that there's some basic question I can answer. Yeah, and if you have trouble seeing this, I would recommend you to first think about the simpler case where instead of this equation, we had yj plus 1 is bigger than to the size of yj times half the size of u times half. Calculate it. And here, geometrically, what's going on is very simple. And this would be like the average of yj and u. And actually think of equal to. So it's even better. If you knew this, then you can actually exactly figure out how yj will evolve. And if this was bigger than or equal to, you can have a bigger than. Yeah, and now what we have is a variant of this where instead of averaging with weights half-half, you're averaging with weights 1 minus 1 by k. So that's why you get a slightly slower. So I'll pause here for a little bit.
For slice 10, on the slice 10, can I have a question?
For what?
Slice 10, yeah.
Okay.
What does it mean for u subject y1 over k? What does u
So
subject?
u subtract y1 is the set, the red set in this picture. Okay, it's all of u minus, and you remove the elements of y1. If y1 is totally disjoint from u, then you don't remove anything.
Okay, then what about subtract k, divide by k?
Oh, that's just the size, right? So I have the cardinality. So it's the size of u minus y1 divided by k.
Okay.
So the size of u minus y1 is just some number. That you have to. So, okay, so this is it's a direct argument, okay, and what it shows is that you have this claim, and eventually what it means is that size of yk is bigger than equal to 1 minus k times size of size. So if I put j equals k, this is what I get. So if I put j equals k, this is what I get. And yeah, and for those of you who remember this is a number that converges to 1 by e. Okay, so this is a calculus fact that hopefully all of you have seen at some point. And actually, if you plot it out, it's very easy to see. For k bigger than or equal to 2, it will approach 1 by e from the top. So this tells you that it's bigger than or equal to 1 by e. This is 4.6. So this completes the proof, right? So what it says is that each time you cover at least a reasonable number of new guys, and that number you're able to bound by the distance to the optimum. And this turns out to be like a nice way of showing. Okay, so this works for a few problems where you say that in some sense you want to maximize some function. You assume that if there was some optimal choice that produced the value of u, then your greedy choice at each time will produce something that is a reasonable fraction of what is remaining. So that's one way to think about it. Okay, so yeah, so that's how you think about it. Yeah.
So why did we assume k equal to 2 and like could you explain how this is?
No, the assumption of k equals 2 was not for the whole thing. I'm just saying, suppose you see this recurrence for the first time, you may be a bit baffled about how to analyze this, right? Just so in cases like this, you should think, how would I have analyzed it if k were 2? Okay, that's all I'm saying. Okay, and then you see a nice geometric interpretation. Like if k was 2 and yj was equal, then that is the equation you would have had. That has a clean geometric interpretation, in the sense that each time you have this target u, and each time you're moving to the average of the current point and the target, and you keep doing that, which means you will approach this target in a pretty fast way. Right? And now instead of just the simple average, you have a weighted average, where you're still kind of closer to this, but you move by a reasonable factor. Yeah, and that's what's going on. So yeah, so that was that half thing was just an example. And in general, this is something you should keep in mind. If you've got a equation that you cannot analyze, you try to plug in simpler values and try to see how you will analyze those simpler things. Right? And yeah, so that's what I was implicitly doing. Right. So, but yeah, that's a good point. Okay. All right. So this is good. Right. So now let's look at a different kind of a paradigm. Okay. So it's a slide. So this kind of completes what I wanted to say about greedy algorithms. And note that we've seen three different kinds of analysis. Okay, like two of them were direct, and one had more structure. So, all right. So as I said, so a summary of greedy algorithms is basically that keep building up a solution. Often the algorithm is easy to come up with. The analysis is tricky. Okay, hopefully, all the examples we've seen illustrate that point. Okay, and yeah, so that's and often you don't find an optimal solution, but sometimes you might find something that's not too bad. So that's the thing about greedy algorithm solution. So now we'll ask a slightly different question. This is probably more relevant in practice, right? So you may try an algorithm. Let's say you try some greedy algorithm, and you don't find an optimal solution. Now, you can ask, can I improve this solution in some obvious way? Okay, and can I keep improving it so that I get to something that is reasonable? So for this, I wanted to go back to the example we saw when looking at greedy algorithm, when we introduced greedy algorithm. Right? So the example is this matching problem. You've got a bunch of children, bunch of gifts, and happiness values. Okay, so this matching problem will show up a lot in the class. So it's because it's a nice problem that captures many things. Then we said that sometimes the greedy algorithm was essentially going. So these are children. These are kids. And this was assigning gifts to children one by one. And this was sometimes making bad choices, right? Like the gift could have had enormous value to some child, and maybe had a little bit higher value to child one. So you assigned this gift to child one, and now this is gone, right? So this was the kind of issues we were having. But now you could always do some kind of improvements to such a solution, right? Like suppose you made an assignment like that. You came up with some solution. Or you could say, I can improve this solution in some obvious ways, right? So what would be one reasonable way to improve your assignment? Like you have some assignment of children to gifts. Maybe this guy like this. Something like that. Yeah.
So rather than looking at it as an individual child that makes them happy, look at it as a pair. So you want to find out what grouping of one child and one gift gives us the maximum for all the children and all the gifts that are available. It's like you want to get the 100 first.
Right. So yeah, so you might say, okay, suppose I want to add this 100. Right? And now what do I know? I know that I could not have assigned this guy to this anymore. Right? Because otherwise you can't assign the 100. And then so you've got to assign this guy to some gift. Which one would you assign it to? Like he still has to get something. So what is an obvious choice if you don't want to make too many changes? Sorry?
You can just swap the gift. So like say
Yeah.
child 2 there, we give child 1's gift to him, and we just take child 2's original gift to child 1.
Right, so that's what he also was saying. So this is a natural choice, right? Like you see that maybe there were some edges that were heavy that were left out. So you say, okay, I'm going to cancel these two guys. Then I'm going to swap the gifts of these two children. So this is an obvious way you can try to improve a solution. Right? So what you are doing is check if there exist children I and j. So you don't necessarily need to do it for heavyweight items, right? You can try to do it for all of things. Because you have some assignment, you can just say, hey, for every 2 children I and j, I'll see if exchanging their gifts makes the total happiness value high. So you can do this. If there exists children I and j, such that swapping gifts improves the total happiness. So now the question is how long, one question you could ask is how long this would take. And turns out to be somewhat tricky, but let's assume that it's that you don't care about the time for now. Okay? But let's say you end up with a solution where if so, let me complete that. Swap and repeat. Okay. So you repeat it a bunch of times, okay, and you will end up with a case where you can't find any improvement, right? So this sort of a procedure is called local search, okay, where you have a bunch of moves that you define. In this case, the moves are like swaps between solutions. So this is a meta local search algorithm. So you have a solution. Okay, so you start with a solution that you find somehow, and then you move to some neighboring solution. That is better. Okay, and then you check if there's some neighbor of that which is better. And by neighbor, I just mean, in this case, a neighbor just means a new solution obtained by swapping gifts to 2 children. Okay. So this is a different solution that you can obtain. And now you can check if there is a neighboring solution that improves that, and so on. Okay. So this is the algorithm. You'll never have cycles, of course, because you will only move if you strictly improve the cost of this. So you'll not come back to the same solution. This procedure will eventually terminate. Okay. So Right, so that's something we've got to make sure. Right? Like you can't just keep moving to negative. Yeah.
Is it possible that you move to a neighbor that's worse, but then you so get to a neighbor that's a lot better than first?
Yeah, so this is the usual thing about local search. So we'll come to this, right? So yeah, we will come to this. Yeah, this is the reason local search doesn't always find the optimal solution. So yeah, but this is the general procedure though. So you end up with a solution that is what is called locally optimal. Okay, so in the sense that none of the neighbors have a cost that is better than the solution. What if we cannot improve? So this is we are at a solution where for all ij, swapping here does not. I mean, it only makes the solution worse intuitively, but they could be equal. So let's just say does not make the solution better. Okay. And so, can you write down a mathematical condition for this? Okay, so what is yeah, so in some sense, what are we saying? So a solution is defined by, so this is child 1, child 2, child n, and you have n gifts. So this is so a solution is just some assignment of children to gifts. Okay, so let's say that child I is assigned gift phi I. So phi is the standard term people use for a permutation. That's the reason I'm using it. Right? So if you want to write pi, where p is a permutation. Okay, so you have some permutation of the indices I1 to In, which I denote by P1 to Pi. And I'm assigning child I the gift P sub I. Now, right, so what is this is P1, and let's say what is this P2, but it's a permutation. So how would you mathematically say that assigning gifts to these guys, what would be a formula that captures this condition? For all ij, swapping gifts does not make the solution better. Okay, remember you had these happiness values hij for i. If I'm asking something I simple. So you have these happiness values. Right? So what is the happiness of child I at this point, or child 1 at this point? Yeah, so child I is assigned the object pi. So by definition, the happiness value is h I p sub I. And yeah, so this is just the this is how the h's were defined. Okay. So this is how we have this. And now you know that h I p I plus h j p j. So you know that this thing, this is the happiness we currently have, is at least as large as the happiness when we assign I to pj plus h of j to pi. So this is a mathematical way, I think this is the equation that captures the fact that swapping does not improve the solution. This is just by the definition. So now we want to argue that if we have this kind of a solution where this equation holds for, solution is basically a P. Solution is a permutation. Way of, if you have a P such that this equation holds for all I and j, you want to claim that its cost is at least half the optimal cost. Okay? So there's some optimal assignment, which so let's call the optimum assignment. We call this assignment P, so therefore let's call optimum assignment Q1, Q2 up to Qn. Okay, so this was the optimal way of assigning 1 to 2, 2, 2. So there would have been an optimal assignment, which is also some permutation Q. And I'm saying that the cost of my solution, which is H1 P1 plus H P2 to H and P is at least half of H1 P1. And this is what I think. Okay, and yeah, so it turns out we can prove this very easily using this inequality. And yeah, so I'm not going to show this now because we're out of time, but you will see this in the notes. Okay, so this turns out, this is what we want to show. Okay, so for any choice of this optimal assignment, whatever we have picked is at least half. And yeah, you can see this pretty easily.